Hi everyone. This video is going to introduce and discuss one of our key capital budgeting tools, the internal rate of return, or IRR. Unlike NPV or net present value, which assumes that we know in advance what the firm's discount rate is, often its cost of capital, IRR is instead just going to use the cash flows delivered by a project in order to calculate what the rate of return the firm earns on its initial investment in the project is. Then later, we're going to compare that calculated internal rate of return to the firm's discount rate in order to decide whether the investment generates sufficiently high returns. So, IRR, internal rate of return. Three key questions that capital budgeting tools are going to sometimes pose and seek to answer in order to decide whether or not to invest in a project. The first, how much value does the project create, or how much money does it make in excess of the cost of funds? That's going to be the net present value. Second, what's the project's return on investment? That's what we're going to calculate here, the internal rate of return. And we could also ask how long it takes for a firm to recoup its initial investment in the project, and that's what the calculation of payback period is going to be. This video is focused on IRR, the second tool. So back to a simple example. Suppose that we have a very simple investment project which involves putting $100 million in today in order to return a positive cash flow of $120 million 2 years from now. So the project seems to have generated $20 million of incremental positive cash flow. The benefit in pure cash flow terms is $20 million greater than the cash put in today. But of course, investors had to wait, and there's probably some risk involved in generating that $20 million positive cash return, cash-on-cash return. So what the IRR is going to ask is basically what is the rate of return on that initial investment of $100 million. Given that it took 2 years to turn the $100 million into 120, we can answer that question using our most basic time value of money tool in Excel. For a single payment security, we could use the rate function. So if I move over to Excel, I could just ask, what is the rate of return over the course of 2 periods? So that's the number of periods, with no interim payments, so no cash flows positive or negative delivered along the way, of putting in $100 million at time 0, so that's going to be a negative $100 million present value cash flow, to generate $120 million in positive cash flow 2 years later. And although Excel shows the answer as 10%, we should not be surprised that that's not actually the exact correct answer. If I show some additional decimal places, I can see an approximate rate of return of 9.5%. Why do I say that I should not be surprised that the answer is not 10%? Well, of course, 120 or a $20 million positive cash return on the $100 million investment over 2 years involves some compounding. And so even though we got 20% more cash than we started with, we should not expect to see an annual rate of return exactly equal to the 20% divided by 2. Indeed, we don't. So the rate function can answer those questions as long as our cash flow pattern fits the very, very simple template that allows us to use the rate function in Excel. In particular, if there is just one initial cash flow, one final cash flow, and any extraneous cash flows along the way comprise an annuity, that is to say they're equal and equally spaced, typically that's not going to be the case. So when we move to more complex examples and try to understand what the rate of return on the project is, we're going to have to use more sophisticated tools in Excel or on a financial calculator. That's going to allow us to calculate an internal rate of return that we can plug in to the internal rate of return investment rule, which says accept any project that delivers a higher rate of return than investors could earn elsewhere. And we typically call that the hurdle rate. Where do we get that hurdle rate? Well, for most firms, we're typically going to use the firm's weighted average cost of capital as the hurdle rate. So even though what we're considering is the firm's investment decision, given that the money used to invest in projects comes from the firm's external financing, and the funds generated by those projects get paid out through the firm's payout decision, perhaps as dividends or coupon payments, we're going to use the rate of return that the firm's external capital providers or investors require as the hurdle rate to which we compare our IRRs, and that's going to be the firm's weighted average cost of capital, or WACC. So how do we calculate the the internal rate of return with a more sophisticated stream of cash flows, those that don't just comprise an initial cash flow, a final cash flow, and equally spaced equal cash flows in between that form an annuity. Well, we can't use the rate function. We instead have to use Excel's more sophisticated IRR, or internal rate of return function. And what the example on the slide does is it moves to an example that we could also evaluate an NPV on. That's included on the slide, and I'll show you again how we do that in Excel, and then we'll calculate the IRR. So if we move back over to Excel, we've got the cash flows that are laid out. This hypothetical project involves two initial negative cash flows. So there's an initial outlay that's made not only in year 0, but also in year 1 of $100 million invested in year 0 and $70 million invested in year 1, with two positive cash flows or benefits associated with the project kicking off positive cash flows of $150 million and $100 million respectively in years 2 and 3 before the project is entirely over at the end of year 3 is what's assumed. So if we assume a discount rate of 9%, if we know what the firm's weighted average cost of capital is, we can calculate the NPV using Excel's simple NPV function, where we plugged in first the rate of return required, or the discount rate, in this case a reference to the 9% cell. Then we included a reference to all of the future cash flows that the project generates, which, note, in this case are not all positive. So there's a negative cash flow in year 1 associated with continued investment required after the initial year 0 investment. But the NPV function in Excel expects only future cash flows. All the cash flows get discounted, and so we're going to have to add in at the end in cell C2 the year 0 cash flow, which of course won't get discounted at all. So plugging those numbers in, we see that this project has an NPV at a 9% discount rate of $39.25 million. And because that's a positive number, the NPV rule suggests that we should indeed do the project. So this project is going to get a green light if we think about using kind of a traffic light scheme. So what does IRR do? It asks, what is the rate of return on all of the money put into the project, which in this case includes both the $100 million invested in year 0 and the $70 million invested in year 1. And we can calculate that in Excel just by typing in equals IRR and putting in the values of all of the cash flows kicked off by the project. So we're going to select all of them and close parentheses. Now, I would note that Excel has an optional additional argument called guess. The problem of calculating IRRs on complex streams of cash flows is actually not a trivial one computationally. And our computers are fast enough now that as soon as I hit enter, Excel will figure out the answer very quickly. In this case, it's approximately 21.4%. But sometimes if you have large numbers of cash flows, here we only have 4, if we have large numbers of cash flows or they do a lot of switching back and forth between positive and negative, Excel might have to do a little bit of work to find the answer. And so sometimes we want to actually just put in a little initial guess. And so we don't actually know what it is in advance, but maybe it's something like 50%. And Excel will use that as its first guess to start its search. And that might help Excel find the answer a little bit more quickly. I'm going to come back to that guess question in a moment when I talk about some flaws with the IRR method of decision making. So we've got an IRR on the project, an internal rate of return of about 21.4%. That means that is the annual compounded rate of return that investors are earning on every dollar that they put into the project. And so given that IRR, that rate of return, is higher than the 9% discount rate, we can apply the IRR decision rule, which says do the project if the IRR is greater than the hurdle rate. And as noted earlier, typically the hurdle rate that we're going to use is the firm's weighted average cost of capital, the same number that we might have used as its discount rate when we calculated NPVs. And indeed, the two rules here both give the same advice, which is do this project because it's IRR greater than hurdle rate and because its NPV is positive. Indeed, the IRR rule and the NPV rule for typical investment projects will always give the same answer. So if the IRR is greater than the hurdle rate, then the NPV will be positive. If the IRR is less than the hurdle rate, the NPV will be negative. And at the knife edge case, where the discount rate is exactly equal to the IRR, what's going to happen to the NPV? Well, we can in fact plug in here as the discount rate, the 21.4% IRR that we just solved for. And if we do that, if we put in 21.4% as the discount rate, you'll note that the NPV is exactly equal to 0. So it's showing up as red because Excel doesn't know whether to do just slightly more or just slightly less than 0. But this is really a true 0 solved by Excel way out to an arbitrarily large number of decimal places. So that's not just a mathematical convenience, it has to be true mathematically. This, in fact, is the definition of the IRR. So we give a sort of an intuitive definition before when I said the IRR is the rate of return that the firm earns on dollars invested in the project. But given that the NPV is the amount of value that the project creates in excess of the discount rate, if the IRR, the rate of return on the project, is exactly equal to the discount rate, then by definition, the firm should not be creating any additional value with the project. And indeed, a mathematical definition of IRR is the IRR is the discount rate that makes the NPV equal to zero. So I'll say that again. The IRR is defined as the discount rate that makes the NPV equal to zero. And that actually can give you a little bit of an idea why Excel has to do a little bit of work in order to find that IRR, and you might have to put a guess in. So if we go back to the original spreadsheet with the 9% discount rate, this project now has an NPV of 39.25, and you can think about the way that Excel finds this 21.4% IRR is it's basically trying different discount rates in the background. So Excel says, hey, at a 9% discount rate, the project is NPV positive. Let's try something a little bit higher. How about 15%? No, the project is still NPV positive. How about 25%? Oh, now the project is NPV negative. We got to try something in between. How about 20%? Well, let's try 21%. And so Excel is basically just sort of searching around, looking for the discount rate that exactly makes this thing equal to zero until eventually it settles on something that's very close to 21.4% and makes the project's NPV very close to zero. So the IRR rule says, if your IRR is greater than your cost of capital, you accept the project. That means that the project is value creating. If the IRR is less than the cost of capital, then you reject the project. The remark at the bottom of the slide is consistent with what I said before. It notes on the slide that in most cases, the IRR rule and the NPV rule coincide. And what I said earlier was that for typical investment projects, the NPV and the IRR rule should coincide. So if IRR is greater than the hurdle rate, NPV should be positive, and vice versa. So what is this in most cases or for a typical investment project? Well, it turns out that thinking about IRRs in order to make these kinds of decision rules really only kind of makes sense if the firm puts money in upfront and receives benefits in the future. So for a simple two cash flow investment project, that might look like this. Money goes in at the beginning and comes out at the end. Money goes in at the beginning and comes out at the end. For this cash flow, it's a little bit more complicated because money goes in at the beginning, but it happens over the course of 2 years where there are negative cash flows, and then gets paid out in 2 subsequent years where there are positive cash flows. It turns out that this typical investment project, the idea that the IRR rule and the NPV rule coincide, only needs to be true for projects where all of the money goes into the project at the beginning of the project. And so, for example, if we had a project like the one on this slide that does not meet that, we're going to see what happens to IRR and NPV. So suppose, for example, that a firm's required return rate on a project is 15%. So this is a different discount rate that we saw before. And suppose that the project costs $90,000 initially in cash to get going. So there is that negative $90 million cash flow that happens at time zero. There's an initial negative cash flow. But suppose now that the positive cash flows in year 1 and year 2 generated by this project, so a different stream of cash flows than we saw before, are then followed in year 3 by another negative cash flow. So what's going on? Maybe there's some kind of cost that needs to be paid at the end in year 3 in order to dispose of equipment. There's some other kind of shutdown cost. Maybe there was some environmental remediation cost. So we've got to clean up the damage that the project did in some way. Maybe the project was associated with a risk of litigation. But in some way, this project, which costs $90 million initially, kicks off $232 million over the next 2 years, but then costs an additional $150 in year 3. And suppose we want to understand whether we should accept or reject this project. So what I've done here on a tab called Flaws with IRR is I've laid out these cash flows. And if we think about calculating the cumulative cash flows for each year, so if I think about just adding up cash flows year by year, you'll see that ultimately this project has actually lost the firm $8 million in cash. So the firm has put in 240, but it's only generated $232 million. And so we should probably expect this project, I don't know, doesn't look that good. On the other hand, a bunch of the negative cash flow comes at the end, and firms don't mind putting in money as much if that investment is made at the end. So if we calculate the NPV, okay, if we just calculate the NPV for this project, and we do that using the 15% discount rate, then put in all of the future cash flows, not the cumulative cash flows, not the year zero cash flow, but just all of the future cash flows, some positive and some negative, and then add in at the end that extra year zero cash flow, we'll see that this project appears to have a positive NPV, an NPV of $1.77 million. And we could get the same thing just by discounting each cash flow separately. So this would be an alternative way of calculating it, where for each cash flow, we would just discount it for the relevant number of periods. And let's just do that real quick. Oops, wrong kind of parentheses. Let's make sure that we're flipping the signs in order to actually be calculating PVs rather than PV cash flows. Oops. And if we then add all of those up, hopefully what we're going to get is that same positive $1.77 million that make the project look attractive. So despite the fact that this project is actually destroying cash for the firm at a 15% discount rate, the firm is still willing to destroy $8 million of cash over 3 years because they get benefits in year 1 and year 2. They get relatively short-term benefits that outweigh they get short-term benefits that outweigh the $150 million additional, let's say, cleanup cost that they have to pay in year 3. So what happens if we calculate the IRR on this project? Well, if we ask Excel, hey, let's calculate the IRR for these 4 cash flows, the negative 90 through the 150. And again, we're not using, it's critical, we're not using the cumulative cash flows to do this. We're just using the raw cash flows. Excel's going to come up with an IRR of about 10.1%. Okay, and given that 10.1% is less than the discount rate, you might ask, like, why is it that the project is NPV positive if the IRR is less than the discount rate? That seems to go in exactly the opposite direction of what you told me we should be looking for. And so we actually can check what's going on if we calculate the NPV at different discount rates. So here's the same NPV calculation. You'll note that this project is NPV negative at discount rates of, let's say, 1 or 2%. So all that I've done here is I've taken this same NPV calculation, and instead of using a 15% discount rate, I've just used a 1% discount rate, a 2% discount rate. We can check that indeed, if we put in the 15% discount rate that we used before, we're going to get that $1.77 million NPV. But if we copy the formula across to consider a wide range of different discount rates, and then we check a graph, we'll see kind of a funny, interesting thing that's happening. So what this graph is showing is it's just graphing the data that we just put together that shows NPVs at different discount rates. And if you check what happens and you read off the graph, the 15% discount rate that we proposed the firm had originally, it's got a positive NPV. So the project at a 15% discount rate actually looks worth doing. It's NPV positive. So why did the IRR come out to be 10.1%? Well, I told you earlier, the definition of IRR is it's the discount rate that makes the NPV positive. And indeed, you can see on the graph that at a 10.1% discount rate, this project is exactly NPV 0. So this project is break even at a 10.1% discount rate. But if you look at the graph, you'll note it's NPV positive for discount rates greater than 10.1% only until the discount rate is less than, I don't know, something around 43%. And if the discount rate is higher than that, if the cost of funds for the firm is extremely high, then it actually turns out that project goes back to being NPV negative. And this is an additional reason that Excel gives us the opportunity to plug in a guess for IRR. So with no guess, when we calculate an IRR, or if we put in a guess of, let's say, 10%, we're going to get that IRR of 10% that we got here. But if we were to put in another guess, like, I don't know, 40%, you'll see that Excel is able to solve a different IRR for the same stream of cash flows of 42.7%. And what the graph confirms for us is that both 10.1% and 42.7% are IRRs for this project. Okay, so this firm actually, or this project rather, has more than one IRR, and the firm should only accept the project. The project is only NPV positive if the firm's discount rate is in between that range. So what does that mean for how we should think about our IRR decision rule? Well, this is a green light project as long as it satisfies the NPV decision rule, and that's always going to be the case, except if NPV is greater than 0. Okay, so that's really always going to work for us. That means that at a known discount rate, the project is value creating. And as long as we follow that NPV that NPV rule, we should do just fine. Obviously, we had two different ways. Now, our decision rule before was except if the IRR, the rate of return on the project, is greater than the hurdle rate. But it turns out there's a caveat that we need to add, which is this only works if all investment is at the beginning. Okay, so I'm going to call this an orange light. You'll note that the rule actually doesn't work here. We can really only use the IRR rule. Okay, we can only use that IRR rule. The one that we said in the first exercise was do the project if the IRR is greater than the hurdle rate. We can only use that rule if all of the investment in the project happens at the beginning. And as soon as we have a project like this one, where some of the investment happens in the beginning, but then there's additional funds that are required at the end, it becomes unclear whether the firm wants to have a high or a low IRR on the project. So we really shouldn't use the IRR rule to make decisions in cases where cash flows go up and down from positive to negative to positive to negative. We should only use it for what I might describe as a typical investment project, one where you put money in at the beginning and you get benefits out at the end. So you'll be able to see this on the slides, and there's some further discussion. That's where I'm going to end this discussion of IRR, and I hope this has been useful. I'm going to have another couple videos where we're going to lay out the third tool payback period and then try to tie everything back together.